This is the first in a set of videos on modelling. First of all, we're going to look at resistors in series. Now, before we get on with resistors, we might want to summarise the overall aims and objectives for this set of videos. First, we want to develop in students an awareness that many components can be modelled by simple linear equations of the same structure. So you'll see this graph here, and you'll notice it's a simple straight line graph, and the most important point is that the graph goes through the origin. So you can use an equation something like y equals ax, where that was the x-axis and that was the y-axis. And we're going to assume that many components can be modelled by an equation of this structure. Now the interesting thing is that if lots of components have got the same mathematical structure in the model, then perhaps they've got analogous behaviour. And why is that an advantage? Because it means if we understand one component or one scenario, we might well gain an understanding of what at first appearances is a totally different scenario. So in detail, we're going to look at the governing equations for models for some key engineering components. We're going to look at springs, resistors, heat flow through a bar, fluid flow through a pipe. Now there are many other components we're not going to deal with explicitly, but hopefully by the end of these videos you'll be able to deal with those other scenarios by yourself. This video then is going to look in particular at resistors, and we're going to assume that students are familiar with Kirchhoff's voltage law. We'll summarise it in a slide, in a few slides' time, just in case you don't. We're only going to consider resistors in series with a fixed input voltage supply. We're not going to look at scenarios where the voltage is changing. We'll just assume it's constant. Now, Kirchhoff's voltage law states that the voltage is shared amongst the components in the path, and again we'll clarify what we mean by that in a few slides' time. And by a series arrangement, we mean that the same current is passing through each resistor in the path. Now this assumption is fundamental to the conclusions which follow and the next few videos. Let's start then with a single resistor. So we've got an applied voltage V, you can see that here. We've got a current through the loop I, and we've got a resistor R1. And most students will probably know by now that you can write an equation representing this circuit as V equals I R1. I'll put brackets around the R1 so you know it's a single variable. What happens then if we've got lots of components in the same loop? And this slide reminds us of what Kirchhoff's voltage law says. What we need to do first is say, okay, what voltage is going across each component? So we'll put V1 across that component, V2 across that component, V3 across that component. And what Kirchhoff's voltage law says is that as you go round the loop, the voltages across each component must add up to the voltage supplied. So there you can see it in the box there, but I'll write down the exact equation we get here. So here we had three components, so we get V equals V1 plus V2 plus V3. So the voltage drops across each of those components must add up to the voltage difference at this end here. And you'll notice I've not put anything into these boxes. These boxes here, I've not said what they are, because in fact Kirchhoff's voltage law is generic. It should apply whatever components you put in there. Now, I've made a remark here just to be clear that although I've put this as an applied voltage V, and you might consider that's a battery or something similar, in practice you might well have a voltage V1 here and a voltage V2 here, where V equals V1 minus V2. We're not going to worry about that subtlety too much because it is an unnecessary detail. What happens then if we have two resistors in series? Well, what I'm going to do is just complete annotating the figure, and that's one of the things students need to learn, that when you get a diagram, if it's not completely annotated, it's often useful to annotate all the bits that aren't annotated, because that helps you when it comes to the analysis. Now that I've marked the voltages across each component, I can immediately say, Kirchhoff's voltage law tells me that V equals V1 plus V2. However, I also know the equation for the voltage across a resistor, so I can write V1 equals I R1 and V2 equals I R2. And you'll notice what I can do next is I can take this V1 and I can put it in here. I can take this V2 and I can put it in there, and so what I get left with is I into R1 plus R2. So I've now successfully modelled a circuit with two series resistors. So observation. When resistors are placed in series, the overall resistance to current flow increases, so the current reduces. And you'll notice this is what we had with just a single resistor, V equals I R1. This is what we had when there was two resistors, V equals I R1 plus R2. You'll notice the effective resistance has increased. This was the current with a single resistor, V over R1. Here's the current with two resistors, V over R1 plus R2. So the current has reduced, resistance increased, current reduced when you add another resistor in series. What happens then if we have three resistors in series? Well, again, the first thing to do is annotate your diagram. So let's put our voltages across each of these components, V1, V2, V3. Then I'm going to write down Kirchhoff's voltage law. That's always a good step for series. So V equals V1 plus V2 plus V3. Then I'm going to write down what are the equations for each of these resistors in turn. So I've got V1 equals I R1, V2 equals I R2, and V3 equals I R3. And again, you'll notice same current going through each of these resistors, and that's quite useful because it means I've got the same I here, here, and here. So now, exactly as on the previous slide, I'm going to take this V1, put it in here, this V2, put it in here, this V3, put it in here, and what I get left with is I into R1 plus R2 plus R3. So the observations again. If you put lots of resistors in series, then the resistance increases and the current gets smaller. So you'll see three resistors in series. I get this model here, V equals I R1 plus R2 plus R3, or I is V over R1 plus R2 plus R3. And hopefully it's obvious to you that if I was to put many resistors in series, I just extend this bracket, so I can have R1 plus R2 plus R3 plus, and so on. And therefore the current gets smaller still, because every time I increase this R, then because I equals V over the total resistance, I must decrease. So in summary, resistances in series add to give the total circuit resistance, and there's your formula. You can see I've just added all the resistances to get the total circuit resistance. The greater the resistance, the lower the current flow for a given voltage supply. And a reminder at the bottom, it's implicit in this video that the same current is passing through each component, and you could argue, well, that's a definition of a series arrangement anyway.